Okay. My statement is basically that if we are able to calculate cyclic plastic deformation, that would be a big step towards understanding what's going on with RCF initiation.
Okay, thank you. The second speaker, please.
Okay, thank you. Very quickly, I think contact tables are a very good tool for computing real contact forces in railway dynamic simulation environment. They have been not so much used in the recent past. They were used rather in the 70s and so on, but it's probably time to think again about using this tool and to this end to extend it to non-Hertzen conditions.
Yeah, so
Okay.
speak, please.
Yeah, from our model, it looks like local plasticity decreases the coefficient of friction at high levels of pressure.
Okay. Actually, I repeated my statements. So I just asked some more information. The question I really want to answer is, we observed corrugation, not everywhere, but the vibrations is everywhere. No matter it's pimping, it's vibration excited by welds, it's always there. But not everywhere has corrugation. So that's my explanation. Thank you.
Okay, so I give Glasses the priority. Ask the first question.
Okay. I'll ask a question first to the first speaker, I think, but others could comment if they like. The characteristics of your shear flow and so on for your 2D and 3D simulations are very similar. The way the shape, the way the curves look. Do you think it would be possible to do a 2D calculation and scale things like the pressure or the material characteristics to bring the 2D curves and the 3D curves into line and then get the benefits of computational efficiency, but also representing what happens in practice? Is that
You're right, that would be an interesting idea. The only thing that kept us from doing that yet is that we're leaving kind of the basis of physics, because it's then everything is like that. And up to now, it's more or less we're safe. And finite elements is anyway will never be as fast as other methods. But you're absolutely right, that would be one of the things we try. Applying contact patches, trying to do that in 3D, maybe just with applying contact patches, and then thinking about what do we have to change with the plasticity model to do it also in 2D. Yeah. But this effect of the sides of the contact patch, they kind of hinder the plastic deformation in the direction, and this is very hard to capture in a 2D model. And if we change that, then it wouldn't fit anymore.
I'll come back. I'll leave somebody else to have a go.
I think computational efficiency was a theme of most of the talks here. I mean, you're just way crazy fast for your calculations. But I was, particularly the last speaker, how long was your simulation taking to run?
We run about 3 meters rolling distance, and it takes about 40 hours.
Yeah.
Yeah.
Yes. So that is why you didn't look at different wheel profiles or so many different...
I think that is the profiles. We have tried that if its influence on the resultant force and also the wear pattern is not really important in this case. But it indeed influences the magnitude. Yeah, but here we really to try to understand the influence of traction. Yeah, that's the basic key.
Okay, and for the first speaker, you're looking for the flow along a large section of rail.
Mm-hmm.
So I didn't understand why you weren't happy just ignoring the bits at the beginning and the end that were different.
The question was, is there a region where it's constant and not influenced by the ends? And for the 2D models, it was actually that the beginning and the end would influence what happens in between. So we had to make sure that we have something which is not influenced by that.
Okay, yeah, please.
Okay, I want to follow up on the question to the fourth speaker about computation time. I know you like finite elements a lot and you built this model, but what other benefit is there of using finite elements over multi-body simulation for the test cases you describe here?
That's actually a very good question, by the way. For finite element, the most important advantage, in my opinion, is it can calculate the continuum vibrations. The continuum vibrations may be important at high frequencies dynamics. That's first. And the second one is with the finite element, you can not only calculate the contact pressure and the tangential pressure tractions. You also calculate the stress inside the wheel and the rail, and which is much more important for damage and wear and product deformation simulations. The third one, I would like to emphasize the actual geometries can be taken into account. So at the high speed frequencies, the wave inside the solid and also other the geometry related the speed, spin, and all these effects can be taken into account accurately.
So in your one of your first slides, you showed time steps of 10 nanoseconds, and the wear pattern of 1 millimeter. That's a frequency of 100,000 hertz. How did you validate your model for those kinds of step sizes and things? How can we reliably understand this is what's happening in practice?
I didn't catch your question.
Does your model solve the scales up to 100,000 hertz, and how do you know?
As I said, the time step is down to -8th power. So numerically, it can down to that area on the frequency. But of course, limited by the element size, it's only reasonable to the frequency is within the time step, the speed passed by the element. So it's the limitation is limited by the element. But our element is only 1 millimeter. So that makes us believe it can solve the high frequency problems. But of course, we don't have a reference for validation. That is true. But we have to live with it. We have to go ahead.
Did he answer your question?
Yes, thank you.
Yeah.
He asked.
Okay, so I have a follow-up for the last speaker here.
Yeah.
So did I understand it correctly that the entire track model is 3 meters long?
Sorry?
Is the track model 3 meter in total?
No. The track meter is about 20 meters long.
20
so
meters.
We have maybe, I didn't remember correctly, 20-something slip spans. It has to be large enough to avoid the boundary effects.
Yeah, that was my question. Have you understood? So 20 meters is enough? Have you validated that?
Yeah, we did. We did it in the past. We compared the results with 20 meters long and with 60, 120, and the result is almost the same.
Okay, in what track response? Because if you compare, for example, acceptance to contact forces and different track or vehicle outputs, the required length may differ.
For our validation, we only consider the contact forces and the resulting stress.
Okay, and in those responses, it was enough with 20 meters?
Yeah, that's also what I was using for.
Okay, thank you.
Okay, thank you.
Okay, the next question should be for the other speakers. Okay, not the first one. We should give the other people the opportunity. So I think, your turn.
I have one question to Stefano about his approach, because this approach is more interested for application for real-time control system, especially on rail vehicles. So how input parameters, or we can say error in input parameters, will be influenced on errors of calculation of creep forces done, or interpolation of values, creep forces with lookup table?
Well, it's an interpolation. It's basically a linear interpolation. So, of course, the farthest you go from the interpolated points, the larger error you may expect. So, in the end, the problem is to find the best spacing of points and the best number of points that will provide you with a best deal between accuracy and...
So I just want to ask, it will be depends, so number of points should be depends on the input resolution.
Yes.
To the table, yeah?
Yes, exactly.
Thank you.
Yes, please.
Wait. My question is for me. After the contact table was created, and this method of the table is suited to different visual profile. For example, the profile is weird, different. All of it is it suited for all of the profile?
Yeah. I think this question relates also to the question that Edwin was asking, and I did not have time to answer. But of course. Now, the problem is, if you have different wheel profiles, you can have non-Hertz and contact conditions, which are highly challenging from the point of view of an accurate description of the total creep forces and moment. Now, you can have different shapes for the non-Hertz and contact. And of course, the SDEC, which I presented, is just one possible shape, and it is good for interpreting some conditions. There are others when maybe the central part of the contact patch gets like squeezed and nearly to separate the contact into two distinct patches, closed patches. That one, this kind of description of the non-Hertz and contact patch is not able to deal with. But our next step is actually to find a different regularization for non-Hertz and contact patches, which should allow also to reproduce, let's say, a wider range of shapes, of non-elliptic shapes, which will, of course, require one additional geometry parameter. So it will add one dimension in the contact table. So it will make even more critical the trade-off between the sides of the contact table and the accuracy. I hope this answers your question, but...
Okay. I have I have another question. The question is about how fast is to use this method. How fast?
Okay, I would say it's a pure interpolation in 5 dimensions, so it is really fast. I would say it is at least comparable to using heuristic formulae like Pollack or like Schoen-Heydrich-Elkins. It's the same, more or less, time required, but I think it is more powerful in terms of addressing different types of contact patches, including non-Hertz.
Okay, yeah. Okay, so unfortunately, you have finished this panel session. I think there's still an issue with the time. Anyway, so let's thank all the speakers